Hello everyone, welcome back to CodeMaster. In today's video, we are going to discuss about backtracking with recursion. This technique helps us solve complex problems by exploring all possible solutions and backtracking when a decision leads to an invalid state. We will break this down step by step with examples, advantages, and limitations, and we will discuss how backtracking works in Python. Let's get started. So let's start with the basics. Backtracking is a problem solving technique that involves building a solution incrementally. If at any point we find that the current partial solution is invalid or won't lead to the correct answer, we backtrack by undoing the last step and trying a different path. Think of it like navigating a maze. You choose a path, but if you hit a dead end, you back up to the last decision point and try another route. This approach works great for problems involving decision making like puzzles, combinations, and permutations. Imagine trying to arrange books on a shelf, and each position can hold only certain types of books. You try placing one, but if it doesn't fit, you take it out and try another one. That's backtracking. Backtracking relies on four key concepts. First one is recursive exploration. We use recursion to explore all possible solutions. Second one is base case, the stopping condition that tells us when we have reached a valid solution or exhaust all possibilities. Third one is constraint checking. We check if the current choice is valid. If it violates the problem's constraints, we discard it. The fourth one is backtrack step. If a choice doesn't lead to a solution, we undo it and try another option. For example, in the nqueues problem, we place a queue on the board, check if it's safe. If not, we remove the queue and try another position. That's backtracking in action. Let's look at a simple example to understand backtracking better. Finding all subsequence of a string. A subsequence is a sequence derived from another sequence by deleting some elements without changing the order. For example, subsequence of A, B, C are A, B, AB, AC, and so on. So this is the code for finding all subsequence of a string. So let's break the code step by step. First, we will find the subsequence. It will take string, current index, and current subsequence as parameters. Then we have the base case. If index reaches the end of the string, which is if index equal to length of the string. If index reaches the end of the string, we print the current subsequence and return. Then recursive inclusion. Here in the first recursive call, we add the current character to the subsequence and move to the next index. Next, in the second call, we exclude the current character and explore the next index. This recursive inclusion and exclusion generate all possible subsequences. So for the input ABC, the output will be ABC, AB, AC, A, BC, BC, and an empty string. These are some of the real world problems solved with backtracking. First one is the nqueue problem. The nqueue problem requires placing n queues on a n by n chessboard such that no two queues attack each other. Queues attack in the same row, column, and diagonals. The approach is simple. We use backtracking to explore all possible placements, then place queue row by row, ensuring the current placement doesn't conflict with previously placed queues. If a valid placement is found for all n queues, store the configuration. If a conflict arises, backtrack by removing the last placed queue and trying the next possibility. The next one is the Sudoku solver. Given a partially filled 9 by 9 Sudoku grid, fill in the missing numbers following these rules. Each row must contain the digits 1 to 9 exactly once. Each 3 by 3 subgrid must contain the digits 1 to 9 exactly once. To solve this Sudoku solver, the approach is simple by using backtracking to fill in the empty cells. Then we'll try placing numbers 1 to 9 in an empty cell. Then we check if the placement is valid based on the constraints. Then if valid, move to the next empty cell. And if a conflict occurs, backtrack by removing the last placed numbers and trying the next option. We will stop when the grid is completely filled. Next is the string permutation. Given a string, generate all possible orderings of its characters. And the next one is rat in a maze. And a rat is placed in the top left corner of a maze and needs to reach the bottom right corner. The maze consists of open paths 1 and walls indicated as 0. The rat can move left, right, up, or down. The approach is simple. We use backtracking as the previous three problems to explore all possible paths, move in each possible direction, and if a dead end is reached, backtrack and try a different path and mark visited cells to avoid cycles. So these are some of the classic backtracking problems which are commonly used. Backtracking can be powerful but computationally expensive. So time complexity varies based on the problem, usually order of 2 raised to n for subsets or order of n factorial for permutations. Space complexity is order of n due to recursive stack space. Optimization tip is like use pruning to avoid exploring unnecessary branches. For example, using a Boolean array to track visited elements. Some of the advantages include simple and elegant. It breaks problem into smaller, manageable subproblems. Systematic exploration, it checks all possible solutions. No need for complex data structures. Then it is versatile and brute force alternative. Some of the disadvantages of backtracking include its exponential time complexity, can be very slow for larger inputs, high space usage, recursion uses stack space, then redundant computation. It might explore the same subproblems repeatedly, that not always feasible, and it is difficult to debug since recursive logic can be tricky to trace. So when exactly to use backtracking? When brute force is too slow, we can use backtracking. When there are multiple possible solutions, we can use backtracking. When constraints need to be checked dynamically, we can use backtracking. Some example use cases are for solving puzzles like crossword, Sudoku, etc., generating combinations and permutations, pathfinding problem in AI and robotics. So some real-world examples include web crawling, file system, data parsing, AI and games, solving mazes, game state trees, and puzzles like Sudoku. So let's summarize what we have learned today. Backtracking is a recursive approach for exploring all possible solutions. Some key components include recursive exploration, base cases, and backtracking steps. Then some example problems, finding all subsequences of a string. We discussed about the time and space complexity. We discussed about the real-world applications from puzzles to decision-making algorithms. So in the next video, we will be starting with introduction to hashing and hash maps. So that's it for today's video. If you enjoyed this video, don't forget to like, share, and subscribe to CodeMaster for more coding tutorials. See you in the next video. Happy coding.